Hello, everyone. Welcome to this next video in which we will see how can we go from the Navier-Stokes equations for an incompressible flow to the famous Bernoulli's equation. The main assumptions on the problem are essentially that we're looking for a steady state flow, so the solution will not depend on time. Also, the next assumption is about the inviscid fluid, meaning that we assume that there's no viscosity on the flow. And then we'll say also that this is a potential flow, meaning that the velocity field is given as the gradient of a scalar field. And the other one, which is also important, is the one that says that the only external force that we have considered is the weight itself. So the force that is actually given by density times gravity, since these equations, remember, are given per unit volume. Okay. A very important tool that we will use for this derivation comes from index notation. Index notation is essentially, or something called Einstein's notation. It is a notation that simplifies the way how we treat sums. So think of it this way. You have a vector that can be expressed as the components, the sum of their coefficients and the unit vectors along the main directions on the flow. This is, of course, a case of a 3D flow. Instead of writing this down like this, we can write it down as a sum from I1 to 3 of Bi Ei hat. But the Einstein's convention or index notation convention says that we can essentially omit the sum symbol by knowing that whenever we see two indices which are repeated, like in this case, that indicates sum. Okay? That's the whole point. Along the main properties that we will use, we can mention the property that says that the indices which are repeated are called dummy indices, in the sense that you can replace the two indices which are repeated by a different index, say from II to KK, and it will not change the meaning. Okay. Another important property which we must mention is that there's no such thing as more than two repeated indices. That is not allowed. So two indices on the same, say, tensor, second-order tensor is allowed. Three indices is not. Okay. And the final tool that we will use is the permutation symbol, which allows us to write down the cross product between two vectors in a very simple way using the properties of index notation. Okay? All of that being said, let's go back to the linear momentum equation, which we see here. Remember that we said that this was a steady state problem. So here we have 0. There's no viscosity, so this one is 0 as well. And we also say that this is basically given by negative rho gravity times the unit vector on the third direction. Assuming, of course, that the horizontal plane is the one and contains the 1 and 2 directions, like the first and the second directions. And the third direction is perpendicular in the vertical, normal to that plane. Okay? So that being said, this equation simplifies to rho, the gradient of velocity applied in B, equals negative the gradient of the pressure minus rho times G times the unit vector on the third direction. Okay? So the whole key idea is on this problem is how to express this in a more useful way. And we will do that using the tools that we just developed. So we will express this in terms of a potential of some sort. Okay? And we'll start by the simple calculation and say that what is the cross product of B with the curl of the velocity? Using the notation we just mentioned before, the cross product between the two vectors. We know that this is the permutation symbol ijk times the ith component of this vector times the jth component of this vector times the unit vector ak hat. Next, we will apply the same the same argument of the cross product, but between the nabla operator and the vector b. That essentially gives us epsilon ijk times bi times. Inside this, we can now take this as the epsilon m n j. Then this will be a derivative, which we will take as a symbol delta m b n. And since this is just talking about the component, there's no unit vector here. Okay, and then the unit vector that we have is precisely the ek hat. Okay, then we can take the two permutation symbols all together and say that this is epsilon ijk times epsilon nj times bi partial of bn respect to bn times the unit vector k hat. Okay. Now, next, we will use a property of the permutation symbol that says that if you have epsilon I, j, k, this is the same as having epsilon k, sorry, it's epsilon k, I, j, and this is the same as having epsilon j, k, I. Put in other words, you can move the last one to the first position. You can move the last index to the first position, and you can keep doing it as many times as you want, and that will not change the permutation symbol. Okay? If we do that on the first one here, we will move k from last to first. This becomes epsilon k ij times epsilon m and j times bi partial of n with respect to n e k hat. All right. Next, we will use another important property that says that epsilon k ij times epsilon m and j, when the two indices here coincide, as you can see here, that is equal to the Kronecker delta of Kn times the Kronecker delta of In minus the Kronecker delta of Kn times the Kronecker delta of In. Okay, so notice that the first one takes the first with the first, so I will have delta Kn. Then the second delta is In right here. And then we swap between m and n. So you have Kn, Km, sorry, there was a small mistake here. This is Km and In, okay? So that's essentially it. We will do that here exactly here and say directly that this is delta Km, delta In minus delta Kn, delta Im. And all of that times Bi, delta M, Bn, ek hat. Then we will use the property of the Kronecker delta that says that if you have, say, Aij delta Kj, this Kronecker delta does is these two indices cancel out, and this one replaces the repeated index, meaning that Aij times delta Kj is essentially Aik. All right? If we do that here, you see that here you have Kmin. So here in the first factor, m will be replaced by k, and n would be replaced by I. So we'll have bi partial of respect to k, sorry, bi ek minus, and here the two will swap places, and this is then bi partial of di bk ek hat. Okay? And finally, we see that this is like the derivative of the, let's say, this looks like a lot like the derivative with respect to x of, say, y squared. So what is that? That's going to be 2y dy dx. If we apply that idea here, we can see that this is effectively the partial derivative with respect to k of 1/2 of bi squared, all of that ek hat, minus, and that the term in here can be seen if you notice, this derivative applies only to the vk term. So this would be like the partial derivative of bk with respect to xi ek hat. So very quickly, it can be seen that this is basically the gradient of 1/2 of bi with bi can be seen as the norm of vector b squared minus, and this term here can be recovered as the gradient of the velocity times the velocity. Okay? We also remember that if you recall, the velocity is a potential flow, right? So if you recall, the curl of the velocity is going to be the curl of the potential. And this is a very classical term, a very classical property that says that the curl of a gradient of a scalar field is equal to 0. Okay? So in the end, what we were able to prove is that, well, first things first, this is 0. Therefore, what we've proven here is that this thing is equal to 0. Therefore, we've proven that the gradient of B applied in B is nothing but the gradient of 1/2 of the velocity, the norm of the velocity squared. Okay? And this is a very important term that we will use next. So, and what comes next? We need an additional assumption that says that this is a steady state flow. So the path lines, or let's say the particles, will follow these trajectories on this. Let's say a particle starting at this point will follow this trajectory. Particles starting at this point in the flow will follow this one, and so on the other paths. So what we will say now, what we will do is recall the equation we had before. Rho, we now know what this is. So instead of the gradient of B applied in B, we can say that this is the gradient of 1/2 of the norm of B squared. And that's equal to negative the gradient of pressure minus, and now I'm going to write it down, the term that we had in here as negative rho g times the third unit vector. That is easy to see, that can be expressed as rho g, the gradient of x3. Okay? Since everything is constant, I mean rho, not everything, rho and g are constants, we can take the two terms on the right-hand side and put them on the left-hand side and take the constants inside the gradients to see that this is nothing but the gradient of rho over 2, the normal velocity squared, plus the pressure, plus rho g x3, and all of that is equal to 0. Okay? Finally, what we will take is, let's take a particle, say x of t and follow it, and follow the particle downstream, okay? This is what we are going to do. So say, for instance, we'll take a particle here. We can call this 0.1, and we'll follow it across the flow until 0.2. We can say that 0.1 is taking a time t1, and 0.2 is taking a time t2. And the idea is to find out what happens between t1 and t2 with this equation. And for that, I'm going to recall another idea from calculus that says that the derivative with respect to t of a scalar field depending on a vector field, which in terms depends on the time, by the chain rule, this can be seen to be the gradient of that vector field, I mean scalar field, applied on the point, dot product with the time derivative of the vector field, of the, let's say, the trajectory of the point, okay? So that's basically what we will do next. So we will take the gradient of rho over 2, the norm of b squared, plus the pressure term, plus the internal energy or potential energy term, dotted with the time derivative of this particle trajectory, okay? And by the previous property, we see that this is exactly the time derivative of what's inside the parentheses. So it's rho over 2 velocity squared is the normal velocity squared plus pressure plus rho g times x3. And if you recall, the right-hand side was 0, and so it's still 0. Not 0 as a vector, but now 0 as a scalar, okay? So then the last thing that we will do is let's integrate this from t1 to t2 on both sides, right? And if we do that, of course, the right-hand side will keep being 0, right? There's nothing to be integrated on the right-hand side. But on the left-hand side, what we have is basically rho over 2, the norm of velocity squared plus pressure plus density gravity x3. And all of that evaluated between t1 and t2 is equal to 0. Okay? Finally, that means that the terms that depend on time, which are in theory, in principle, velocity, pressure, and the position x3, must be evaluated on those positions. And then we can say that this is rho over 2. The velocity evaluated at point 2, we can call that v2, plus the pressure evaluated at point can be called p2, plus rho g and x3 evaluated at t2, minus the other term in the lower limit, which is rho over 2 velocity 1, normal velocity 1 squared, plus p1 plus rho g x3 evaluated at t1, that's equal to 0, which finally gives us the result we were looking for, that rho over 2, the norm of b2 squared plus p2 plus rho g, the x3 component that evaluated at t2, equals rho over 2 velocity 1, the normal velocity 1 squared, plus p1 plus rho g x3 evaluated at p1, which is, as you may recognize, the Bernoulli's equation. Okay? So now we can use this equation knowing the restrictions under which it's being. But as I said before, for the case of implicit flows, this is a very good approximation on what happens, for instance, on pipe flow inside a steady state Newtonian fluid, with a relatively low viscosity. And we can finally find what happens inside that tube in terms of velocities, pressures, and gravitational or potential effects in terms of gravity. Okay, so this is all I wanted to tell you for now, and I'll see you on the next video. Bye.